Hello viewers, my name is Dr. Ajay, Associate Professor, Department of PCE, Institute of Aeronautical Engineering College, Hyderabad. And today's topic is definitions and terminology on radio wave propagation 1. So this topic belongs to the course Antennas, Waves and Propagation, and this is from Module 5 of Antennas, Waves and Propagation. And today's topic is radio wave propagation 1 and 2. Both we are going to discuss in the definitions and terminology. So let us start our session. So here there was a scientist by name Maxwell. So Maxwell, he discovered that this time-varying electric and magnetic fields together gives rise to electromagnetic waves traveling with the velocity of light. So whenever we give some input current to any conductor, the conductor will produce the electromagnetic waves. These are time-varying electric magnetic fields produces the time-varying electric and magnetic fields are produced by the conductor, and whatever the radio waves that are produced by the conductor, these will travel with the velocity of light, that is 3 into 10 power 8 meters per second. And later, Hodge, the scientist, he discovered that the electromagnetic waves that are produced by the conductor will travel from transmitting antenna to the receiving antenna in straight path, in straight line only. And here the electromagnetic and magnetic fields that are produced, these will be orthogonal to each other in far field only. So in far field only, the E and H lines of force, or the electric and magnetic field lines of force, will be perpendicular to each other and also perpendicular to the direction of propagation of the wave. And these waves are known as TEM waves. These waves are known as TEM waves. So the three basic paths of the radio wave propagation, there are three. So whatever the radio waves that we are traveling in free space, this will travel in different modes, in different paths. So whenever the radio waves are escaped into the free space, these will travel in three different paths. So as the distance increases, the amplitude decreases. As the distance increases, the amplitude, the field strength of the radio wave will reduce. Hence, we need to study about how these electromagnetic waves will travel in different modes and in different parts of the atmosphere. So these waves may travel in three different paths. One is over the surface of the earth, which we call it as a ground wave. One is in the region of tropospheric region, which we call it as a space wave. And the other one is in the ionospheric region. These waves will travel in the sky and are reflected back to the earth. Hence the name is given as a sky wave. So the three basic paths of the radio signal can take as ground wave, sky wave and the space wave. So here the concept, the power, whenever we give some high frequency current to any conductor, some amount of power resides inside the conductor and some amount of power is escaped into the free space. So the amount of power that is escaped into the free space, we call it as radiation. We call it as the radiation. So in other words, the electric field, the magnetic field, and the direction of propagation of the wave, all are orthogonal to each other. Hence the name is given as TEM waves. So that is the TEM wave, the transverse electromagnetic waves. So whatever the radio waves produced in the free space in the far region, those waves are known as the TEM waves. As we can see here in the figure here, the electric field and the magnetic field both are perpendicular, and these both are perpendicular to the direction of the propagation of the wave. So that is in the Z direction. Now let us see some basic definitions of ray and wavefront. So ray, it is nothing but is just a straight line along the direction of propagation of the electromagnetic wave. A ray is a line drawn along the direction of propagation of the electromagnetic wave. So basically, a ray indicates the relative direction of the wave propagation. So basically, a ray indicates the relative direction of the wave propagation. So a wavefront is nothing but a surface of constant phase of a wave. A wavefront is nothing but a surface of a constant phase of a wave. Such a wavefront can be obtained by joining together all the points of equal phase on the rays propagated from the same source. A wavefront with a surface perpendicular to the direction of propagation is shown in the figure. So whenever we throw a stone inside the water, some circular waves are produced here. These are known as wavefronts. These are known as wavefronts which are having a surface of constant phase of the wave. So whenever we throw a stone into the water, some circular waves are produced So those waves, we call it as a wavefront, a circular wavefront. We can call it a circular wavefront. So such a wavefront can be obtained by joining together all the points of equal phase of the rays propagated from the same source. So there are different classification of waves. The first one is a plane wave. So a wave for which equiphase in plane is known as plane wave. So the surfaces will be the surface of the wave will be equal in a plane, which is we call it as a plane wave. The next one is uniform plane wave. A wave for which equiphase surface is also equi-amplitude, then it is called uniform plane wave. So whichever the wave which is having equal amplitude and also equal phase, we call it as an uniform plane wave. A non-uniform plane wave. So the wave for which equiphase, the phase and the amplitude will not be same or not parallel to each other, then such a wave is known as a non-uniform plane wave. So if we are having equal phase and equal amplitude, then we call it as a uniform plane wave. And if it is a wave is having non-phase or non-equiphase and unequal amplitude, we call it as a non-uniform plane wave. Slow wave. So a wave in which Vp is less than Vc. So Vp means phase velocity. Vp is less than Vc, that is velocity of light. Then we call the wave as a slow wave. So a wave in which the phase velocity Vp it is less than the velocity of the light is termed as a slow wave. Forward wave. A wave that is traveling in the required direction is known as a forward wave. A wave that is traveling in the required direction is known as a forward wave. Backward wave. When a forward wave strikes reflecting surface and returns back, then such a reflected wave is called as a backward wave. Traveling wave. A wave propagating in one direction without any reflection is known as a traveling wave. So a wave traveling in one direction without any reflection is known as a traveling wave. So here the first one is the ground wave propagation. That is the waves which are propagated over the near to the earth's surface are known as ground waves. The waves which are propagated near the earth's surface are called as ground waves. The ground wave propagation is possible when the transmitting and receiving antenna both are closer to the earth's surface. The ground wave propagation is possible when the transmitting and the receiving antennas both are closer to the earth's surface. The ground waves can be further classified as the space waves and the surface waves. So whenever we are going to transmit electromagnetic waves from a transmitting antenna, these will travel in space. These will touch the ground and travel towards the receiving antenna. So these are going to touch the surface of the earth. So this is known as ground. Hence the name is given as ground wave. And these are going in space. Hence this can be categorized as space wave. These are ground waves. We can also call it as the reflected waves or the surface waves. So these are space waves and these are the surface waves which touch the surface of the earth. Sky waves. So what are these sky waves? The waves reaching the receiving antenna as a result of scattering, reflection and refraction by the ionospheric in the atmosphere is known as sky waves. So here the basic ionospheric region, it contains many number of layers, D layer, E layer, F1 layer and F2 layer. So whenever we are going to transmit a signal with some particular frequency, suppose high frequency, about 10 megahertz, it will touch a D layer and reflection happens and the signal is going to reach to the receiving antenna. And we can also increase the frequency for long distance communication. So for long distance communication, if we are going to transmit the signal with a frequency of 20 megahertz, 30 megahertz, the wave is going to go into the sky. It will penetrate into the sky where refraction takes place in the E layer and F1 layer. So after refraction, the wave is going to bend slightly and going to reach to the receiving point. Hence, as these waves are traveling into the sky and returning to the earth, hence the name is given as skywave propagation. The waves that are propagated from sky towards the receiving antenna, we call it as a skywave propagation. So the region of ionization in the atmosphere above 80 kilometers above the surface of the earth is known as ionosphere. Hence the sky waves resulting due to scattering in the ionosphere are also known as ionospherically scattered or ionospherically reflected waves. The region in the atmosphere around 15 kilometers above the surface of the earth is called troposphere. The waves which are reflected or scattered in the troposphere before reaching to the receiving antenna are called as tropospheric waves. So above the surface of the earth, from the distance of 15 kilometers, the region of troposphere starts. So here the reflection or phenomena is going to happen in the tropospheric region. So the waves which are reflected or scattered in the tropospheric region are going to reach to receiving antenna are known as tropospheric waves. So basically, the troposphere is the nearest portion to the surface of the Earth. So the basically atmosphere where we are living is we are living in the tropospheric region, in the region of 0 to 15 kilometers. So here the basic frequencies, there are three different modes of propagation. One is the ground wave propagation, skywave propagation, space wave propagation, whose frequencies are ground wave propagation's limitation is 30 kHz to 3 MHz. So we cannot transmit the high frequency signal in ground wave propagation because more amount of absorption takes place by the ground. Hence, as the distance of propagation increases, the radio wave signal to be transmitted to the receiving antenna becomes zero. Hence, the ground wave propagation is preferable only for short wave communication only. So, as the distance increases, more number of waves fall on the earth, and the earth attenuates the signal. Hence, large amount of signal strength will be absorbed by the ground. Finally, at the destination point, the receiving point, the field strength becomes zero. Hence, the receiving point, no signal is going to receive at the receiving point. Hence, there is a limitation that only low frequency signals can be used in the ground wave propagation, and at the same time, only low frequency signals are used for short distance communication in the ground wave propagation. And in the skywave propagation, we are going to use the 3 MHz to 30 MHz frequency signals, high frequency signals from 3 to 30 MHz. These are used for point-to-point communication, large distance communication. The range of the space wave propagation, where we can propagate signals of frequencies 30 MHz to 300 MHz, is used for TV transmission and FM transmission. So in space wave propagation, it can be effectively utilized the bandwidth range of 30 to 300 MHz for TV transmission and FM transmission. So ground wave propagation, it is particularly important for low frequency and medium frequency. You can see in the figure here, the waves are traveling over the surface of the earth. The ground wave signal is ideally for relatively short distance communication on these frequencies during the daytime. So the ground wave propagation is provide relatively local radio communication coverage only. So local radio communication can be used effectively by use of ground wave propagation. So ground waves are limited to very low frequencies, hence these require large antenna. So whenever we are going to transmit antenna here, the signals, the distance is, suppose, let us say, we are going to transmit a high frequency signal. Suppose we are going to transmit high frequency signal. For high frequency, F is high, then lambda value will be very less. Lambda value will be very less. Hence, the lambda value is very less, the more number of waves fall on the earth. More number of waves fall on the earth, a large amount of attenuation is going to happen. Large amount of attenuation is going to happen. Hence, only 50% of the electromagnetic energy will be reached to the destination, that is the receiving point. So here, this is used for only very low frequency signal. So very low frequency signal. So we transmit a high frequency, only 50% of the transmitted signal will be reached to the receiving antenna as due to the attenuation of the earth here. And ground waves are used to cover short ranges only. These are used for short ranges usually. So here we know that whenever we are going to transmit an antenna, and here there is a receiving antenna, this is a transmitting antenna, and here when we transmit a signal, suppose this is the surface of the earth, here some amount of waves are falling on it. Suppose there is attenuation is happening here. Attenuation is happening here. Suppose here we are transmitting 15 watts of power. Here we are going to receive only 10 watts of power. 10 watts of power is received here due to the attenuation. Again, if the distance is increased, again the more number of waves are falling, and at this point, as the distance is increased from 1 meter to 2 meters, we are going to receive only 5 watts of power here in this point. Suppose if the distance is increased to 3 meters, if the distance is increased to 3 meters, so we are going to receive only 0 watts here. 0 watts. Why? Because as more number of waves fall on the earth absorbs more amount of energy. So as the distance increases, the field strength will be reduced. Hence the receiving antenna, we are going to get only 0 watts of power. So hence the ground waves are used effectively for only cover short ranges only. A ground wave signal is made up of number of constituents. If the antennas are in the line of sight, then there will be a direct wave as well as a reflected signal. So as the name suggests, the direct signal is one that travels directly between the two antenna and is not affected by the locality. The radio signal spreads out from the transmitter along the surface of the earth. So instead of just traveling a straight line, the radio signals tend to follow the curvature of the earth. So this is because the currents are induced in the surface of the earth, and this action slows down the wavefront in this region, causing the wavefront of the radio communication signal to tilt towards the downwards the earth. So polarization, we are going to use in the ground wave propagation only the vertical polarization. Why? Because if we use horizontal polarization, more number of waves fall on the earth. More number of waves are absorbed by the earth. Hence, vertically, always the antenna is vertically polarized in the ground wave propagation. Roughness of the earth. So here, the electromagnetic signal that is going to reach to receiving point depends upon the roughness of the earth. So whether the earth is rough or whether the earth is smooth, it gives really the scientist has given us a formula to determine the roughness of the earth, which is given by R is equal to 4 pi sigma s sin theta I by lambda. Sin theta I by lambda. So sigma s is equal to standard deviation of surface regularities. Theta I is the angle of incidence measured from the earth's surface, and lambda is equal to wavelength. So R is equal to 4 pi sigma s. So we know clearly it is known that R value depends upon the conductivity of the earth. So R value depends upon the conductivity of the earth, or which we call it as a standard deviation of the surface irregularities. Now if we determine the value of R, and if R is less than 0.1, then earth is considered as smooth. If R is greater than 10, the earth is considered as electrically rough. So if R is less than 0.1, the earth is considered as electrically smooth. If R is greater than 10, the earth is considered as electrically rough. Wave tilt. So wave tilt is defined as the change of orientation of the vertically polarized wave at the surface of the earth. So wave tilt is defined as the orientation of vertically polarized ground wave at the surface of the earth. Now space wave propagation. Space wave propagation, it is a type of radio wave propagation in which the radio waves are propagated either directly from the transmitting antenna to the receiving antenna or by getting reflected from the ground. So basically in space wave propagation, direct transmission of the signal is achieved by line of sight communication. So this line of sight communication is also known as LOS propagation. Line of sight propagation is also known as LOS propagation, where we are going to transmit the signal directly between the transmitting antenna and the receiving antenna without reflection or without any obstacles or buildings between the transmitting antenna and the receiving antenna. Space wave propagation is sometimes referred to as tropospheric wave propagation, and we are going to transmit the high frequency signals of 30 to 300 megahertz in space wave propagation. So we can transmit large amount of signal for larger range in the space wave propagation as the frequency is very high. Space wave propagation is used for propagating high frequency signals by permitting direct communication between the transmitting and the receiving antenna. So line of sight. So line of sight is the distance between the transmitter and the receiver, in which if a direct ray passes from the transmitter to the receiver without being intercepted in the earth's surface. So without being intercepted means it means that there are no any obstacles or buildings between the transmitting antenna and the receiving antenna. So in the line of sight communication, the wave travels a minimum distance of sight, which means it travels to the distance up to which the naked eye can see. So we need to employ an amplifier come transmitter here to amplify the signal and transmit again. So the range of space wave propagation, it is given by DLOS, which is given as 4.12 into root HT plus root HR. So this is measured in kilometers, LOS. So the range depends upon the distance between the transmitting antenna and receiving antenna, depends upon the height of the transmitting antenna and the receiving antenna to establish a line of sight communication. So a radio wave propagation, duct propagation. So a radio wave propagation technique that allows the transmission of VHF and VHF electromagnetic waves through the region near the tropospheric layer of the atmosphere is known as duct propagation. So a radio wave propagation where multiple number of refractions takes place in the ionospheric region, hence the name is given as duct propagation or a super refraction. So when we transmit a signal here, as it goes to the any of the layers, so it travels in multiple refractions. Here there is one refraction happening, the wave slightly bends here. Again another refraction takes place, the wave slightly bends here. So after traveling multiple of refractions and reflections, the wave is finally going to reach to the receiving antenna. Hence, the name is given as successive refraction or super refraction. This is direct propagation. So, the direct propagation, the refraction is given by mu minus 1 by plus h by r. This direct propagation depends upon the height of the layer and radius of the earth. And radius of the earth. Fading. So, a reduction of signal strength at the receiving antenna, we call it as fading. Fading is basically undesirable variation in the intensity of the signal received at the receiver. So, fading is basically the undesirable variation in the intensity of the signal received at the signal here. There are different types of fading here. Selective fading, it affects the different spectral components of radio signal with the different amplitudes. Hence, the name is given as selective fading. So, the selective fading is important in case of amplitude modulation. The selective fading occurs when signal bandwidth is greater than the channel bandwidth. So, interference fading. Here, when we are going to transmit the signal, there will be some of the waves which are coming from the adjacent antennas also interfere with the existing electromagnetic waves. Hence, some interference occurs in the free space for a small duration of time. Hence, the signal gets faded at the receiving antenna. Absorption fading. So, due to the variation of signal strength, the different amount of absorption of waves absorbed by the transmitting medium, we call it as absorption medium. So, there are different types of gases and molecules in the free space. When we transmit the signal into free space, different molecules absorbs these electromagnetic waves. Hence, a slight amount of variation of field strength will be absorbed at the receiving antenna. Polarization fading. So, when the sky wave reaches after the reflection, the state of polarization is constantly changing. So, the polarization of the sky wave coming down changes because of the superposition of the ordinary and extraordinary waves. As the distance near the skip range or skip zone, the fading occurs, which is called skip fading. So, due to the variation in the height and the density of the ionized layer, the point at which the wave can be received moves in or out of the skip zone. Thus, due to this, the amplitude of the receiver also varies, producing skip fading near the skip. The next one is the tropospheric scattering. The scattering of energy in a radio wave occurs in the troposphere for a wide range of frequencies between 400 to 5 GHz. 400 to 5 GHz. So, the amount of scattered power depends on the magnitude of variations of refractive index and on the distance over which the variations occur. So, the field strength at large distance normally fall off at a rate of 0.1 to 0.2 dB per meter. So, there are different parameters of skywave propagation. The first one is critical frequency. The highest frequency at which a wave is returned to the earth at vertical incidence, we call it as a critical frequency, which is given by the equation 9 root n max. The maximum usable frequency, the highest frequency at which a wave is returned to the earth for a given distance of propagation, we call it as a maximum usable frequency. The equation is equal to f muff is equal to fc into secant theta I, so which is known as the secant law. So, maximum usable frequency is denoted by symbol f muff, which is depends upon the critical frequency fc into secant theta I. Optimum working frequency, it is known as the between the transmitter and receiver, for which it is defined as the frequency laying between 50% to 80% of the predicted muff between the transmission and the reception points. So, 85% of the muff value, we call it as the optimum working frequency. There is a frequency, next lowest usable frequency. So, there is a frequency which radio communication between two stations will be lost. It is defined as the frequency at which the signal falls below the minimum strength required for satisfactory reception. So, the actual height. So, for actual height and virtual height, the skywave propagation is effective due to the presence of different ionized layers which act as a radio mirror and bounce the skywaves back to the earth. So, when the skywave used for long distance communication reaches a given ionospheric region, the ionization density increases and this in turn reduces the refractive index of the layer. Here, when we transmit a signal here, the signal goes so this is the actual height. So here, from the signal is going to reflect from A, O and B here. and this height O and C, OC, it is known as the virtual height. So where the reflection virtually happens, we call it as a virtual height. So when the skyway bends away from the normal at a certain point, it almost becomes parallel to the layer and bends further towards. Such a wave finally emerges out of the atmospheric layer at an angle equal to that of incidence here. Critical angle, the angle of incidence at which a wave is returned to the earth at a minimum distance, we call it as a critical angle. Skip distance, the shortest distance from the transmitter measured along the surface of the earth at which a skywave of fixed frequency will return back to the earth. So here the shortest distance from the transmitting antenna at which a wave is returned to the earth for a fixed frequency, we call it as the skip distance. Multi-hop propagation. So wave is originated from transmitting T. It reaches to the receiving antenna in different paths. So for long distance communication, we cannot use a low frequency signal. So when we transmit the signal at a high frequency signal, it travels in different layers. So it travels in multiple paths and going to reach to the receiving antenna. So if a wave is traveling in only one path, we call it as single hop propagation. If the wave is traveling in two different paths, more than two paths, we call it as a multi-hop propagation. So this may touch the D layer in different paths, and reflection is going to happen. Multiple reflections are going to happen and are going to reach to the receiving antenna here. Also, it is possible that multiple reflections will happen in many of these layers, E layer and F layer, and finally it is going to reach to the receiving antenna. So for all these topics, let us go to let us refer these textbooks: John D. Cross, Ronaldo J. Antennas and Wave Propagation by Bakshi, and K.D. Prasad, Antennas and Wave Propagation. So let us close the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.